The impossible LED breakthrough that redefines optoelectronics. Researchers have achieved what was long considered unattainable. They have found a way to electrically excite insulating nanoparticles by coupling them to specially designed organic molecules that act as molecular antennas. This hybrid strategy enables the nanoparticles to emit exceptionally pure near-infrared light, ideal for biomedical imaging, optical communication, and precision sensing. The devices operate at low voltages and already outperform many established light-emitting technologies in spectral definition. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. The accompanying conceptual illustration depicts a lanthanide-doped nanoparticle represented as a spider, with its web formed from 9-anthracene carboxylic acid, the organic antenna molecule engineered to trap charge carriers and harvest otherwise inaccessible triplet excitons. Electrifying the electrically impossible. A team at the Cavendish Laboratory, University of Cambridge, has demonstrated a method to inject electrical current into lanthanide-doped nanoparticles, materials that are normally insulators and thus incompatible with standard electronic devices. By tethering tailored organic molecules to the nanoparticle surface, the researchers fabricated the first LEDs built from insulating nanomaterials, an achievement reported in Nature. LNNPs are prized for emitting extremely pure and stable light, particularly in the NIR2 spectral window, which penetrates deep into biological tissue. Yet their insulating nature has, until now, prevented them from being integrated into electrically driven optoelectronic components. These nanoparticles are phenomenal emitters, but we've never been able to drive them electrically, explained Professor Akshay Rao, who led the project. By using organic molecules as antennas, we've essentially created a backdoor, capturing charge and whispering it to the nanoparticle via an efficient triplet energy transfer pathway. Organic-inorganic hybrids solving the insulation barrier. To bypass the nanoparticle's insulating properties, the team created an organic-inorganic interface. They anchored a carefully selected dye, 9-anthracene carboxylic acid, onto the LNNP surface. In the resulting device architecture, the electrical charges are injected into the 9-ACA molecules rather than the nanoparticle itself. Once electrically energized, the 9-ACA enters a triplet excited state. Normally, this dark state dissipates energy as heat rather than light. But here, more than 98% of the triplet energy is transferred directly into the lanthanide ions embedded inside the nanoparticle. This highly efficient transfer produces bright, spectrally pure emission, something no previous electrically driven lanthanide system had achieved. Ultra-pure NIR light at just 5 volts. These new hybrid LNNE LEDs switch on at operating voltages as low as 5 volts. More strikingly, the emitted light has an exceptionally narrow spectral line width, considerably sharper than quantum dots and most other semiconductor emitters. The spectral purity in the near-infrared 2 region is a major advantage, noted Dr. Zhongzhang Yu, a lead author of the study. For biomedical diagnostics or optical communication, you often need a single precise wavelength. Our devices naturally deliver that level of sharpness. Applications: from deep tissue imaging to high-speed data links. The ability to electrically power lanthanide nanoparticles opens a range of high-impact technologies. Biomedical imaging. Tiny, possibly injectable LEDs could illuminate deep tissue, reveal tumors, monitor organ function, or activate therapeutic molecules with high spatial precision. Optical communication. Pure, stable emissions reduce interference and allow cleaner, higher bandwidth data transmission. Chemical and biological sensing. The narrow line width could enable sensors capable of detecting extremely specific molecular signatures. Promising first-generation performance. In initial tests, the LNNE LEDs demonstrated an external quantum efficiency of more than 0.6%, a significant result for a first-generation device based on insulating nanoparticles. The researchers have already identified clear pathways to improve charge injection and energy transfer efficiency in upcoming designs. This is only the starting point, said Dr. Yanzhou Dang. We've opened up an entirely new landscape of materials for optoelectronics. By mixing different organic antennas with different insulating nanoparticles, we can engineer devices with tailored properties for applications we haven't yet imagined. The work was supported by UK Research and Innovation Frontier Research Grant EP-Y015584-1 and Marie Sklodowski Curie Postdoctoral